Today we're starting our new unit on circles, so I'm going to go over a little circle terminology, some of which you probably already know, and then we're going to dive right in and spend most of the time talking about tangents to circles. So here we go. What is a circle? A circle is the set of all points in a plane that are equidistant from a given point called the center of the circle. So if I draw myself a circle up here, all these points that are in this plane that are equidistant from the center, and of course there are an infinite number of these points, right? All those points make up a circle. The distance from the center of a circle to a point on the circle is the radius, as we all know. So all these links that I put here would all be the radius. They would all be the same. Two circles that have the same radius are congruent circles. So if r equals 5 here, and I got another circle somewhere over here, and it's got a, let's do it this way. What if I say the diameter equals 10? I know the radius is half of that, so those two circles would be congruent. The distance across a circle through its center is the diameter, and we got a picture of that I just drew you there. The diameter, the distance across the circle through the center. Okay, a line that intersects a circle in exactly one point is a tangent to the circle. So let me go up here to our circle and add a tangent. Let's say here's the point that line is going to go through, and we got to pretend like that line actually touches that circle. Okay, that line is tangent to the circle, intersects it at only one point. The point where a circle and a tangent intersect, which would be right there, is the point of tangency. Point of tangency. Coplanar circles that intersect at exactly one point are called tangent circles. And I'll draw you a couple of those here. Tangent circles, well, I could draw one right here. Circles that intersect at exactly one point. Tangent circles. They don't have to be congruent to be tangent. Coplanar circles that have a common center. So let's take this. Here's a circle. And if we draw a coplanar circle that has the same center, then we call those concentric circles. Concentric circles, coplanar circles that have a common center. A line or segment that is tangent to two coplanar circles is called a common tangent. So I can have a tangent that's tangent to more than one circle, and it's a common tangent. Okay, so let me draw you a picture of what that looks like down here. A couple of pictures. We could have a common internal tangent. Let me move this guy out of the way. So a common internal tangent might look like this. I got two circles and internal. So let's see if I got a tangent. It's going to point a tangency there. This looks like it would actually intersect the circle twice. That's just because my drawing isn't that good. But this is a common internal tangent. This line is the tangent, and it has one point of tangency on each circle, and it's internal in between the two circles. Common external tangent would look something like this. I missed, but we're going to pretend like I got a point of tangency there on each of those circles. So there's a common external tangent. Of course, I got another one. Got another one down here. Let me see if I can hit it a little better this time. There's another common external tangent. I could have another common internal tangent over here, right? Okay, so there's some terminology. Let's see what's next. Oh, we got a bunch of theorems. So we're going to look at these two theorems here, and then we'll do a couple of practice problems. 12.1 says, if a line is tangent to a circle, so let's look at our picture here. A line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So see here, P is our point of tangency. If we draw the radius, so if we go from the center with the radius to that point of tangency, we know that those two, the tangent line and the radius, will be perpendicular. All right? And the converse is 12-2. It says if a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. So it's just the other way around. If we know that the line is perpendicular at the point of tangency, then we know that it is a tangent. If a line is perpendicular to a radius at its endpoint, so the endpoint of the radius right there, if this line is perpendicular to that, then we know that that line is a tangent to the circle. All right, let's look at our examples. Find the value of x. X is that angle in there at M. And what do we know? We know ML is tangent to the circle at L, and MN is tangent to the circle at N. So from up above, we know that that means these two are perpendicular, right? MN is perpendicular to ON. MN is perpendicular to ON, and also ML is perpendicular to OL. All right, so now we've just got a quadrilateral here, right, that's made by those two radii and those two tangents. So if we got a quadrilateral, we know that the sum of the measures of the interior angles is 360. So we know that x plus 90 plus 117 plus 90 equals 360. And if we go and we solve that for x, we're going to have x equals 360 minus 297, I believe it is. So x is going to end up being 63. And that angle measure is 63 degrees. It's got the degrees right here in the drawing, so I don't have to add it to my answer. Okay, find the radius of circle C. AB is tangent to the circle at B. Okay, so they've already got it marked. That we know that means that BC and AB are perpendicular, so we got a right triangle. So let's see, what are we going to do? I guess we're going to have to use the Pythagorean theorem, right? And that tells us that x squared plus 12 squared equals, the hypotenuse is x plus 8. And of course, we have to square that if we're using the Pythagorean theorem. Okay, we're going to need to FOIL out the right side. So we got x squared plus 144 equals x squared plus 16x plus 64. I think I've showed you guys this trick before, where if I'm squaring a binomial means I got two terms here, 1, 2, then I square the first one. So I square x, I take the two terms, I multiply them together. So I multiply the 8 and the x together, and then I multiply that times 2, and then I square the last term, which would be 8 squared, which is 64. So that's where the x squared plus 16x plus 64 comes from. And if you want to do it this way till you get the hang of it, x plus 8 times x plus 8, you'll see that it does equal x squared plus 16x plus 64. Okay, and if we subtract x squared from one side, those are just going to go away. So now I'm going to subtract the 64. 144 minus 64 equals 16x. And what's that going to be? 80 equals 16x. Therefore, x is going to be 5. So the radius of that circle is 5. And hey, look at that. If this is 5, then I've got a 5, 12, 13. I got an old friend, Pythagorean triple. All right, got some more theorems now. Let's see what they say. If two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. So if I look at my picture here, these two tangents, tangent AB and CB, they share a common endpoint outside the circle. B is outside the circle, then I know that they're congruent. All right, so we got a practice problem here. Circle O is inscribed in triangle PQR. Oh, we know what inscribed means, right? So that means we got 3 points of tangency here. That circle touches that triangle, touches each side once. The perimeter is 88. What is the length of QY? So here's what we're looking for. QY, I'm going to call that X. So let's see, what do we know from the theorem we just looked at? Okay, P, so I've got tangent PX and PZ, they share an endpoint P outside the circle. That means AZ is congruent to AX. And same thing for RZ and RY. Since RZ is 17, I know RY is 17. And I don't know what QX or QY is, but here we go. I do know that the perimeter is 88. So I know the perimeter, which is 88, is the sum of all the side lengths. So I got 15 times 2, which is 30, and I got 17 times 2, which is 34, and then I've got QX plus QY, which I know are congruent, and I called QYX, so I'm just going to put 2X right up there. And now I just got a simple matter of solving this equation for X. So let's see, this is going to be 88 minus 64 equals 2X. So that'll be 24 is 2X. Therefore, X is 12. And of course, we labeled QY as X. So we know that that's 12, and we know that QX is also 12. Okay. Got another one. You're standing at a point R, so I'll just put you here at R. And you're about 4 feet from a circular fountain. So let me try to draw this fountain here. There's our fountain. We'll just call it F, fountain. The distance from you to a point of tangency is 8 feet. So point of tangency, I'm going to put it about right here. And so that'll be 8, right? Distance from me to a point of tangency, or you. And the distance from me to the fountain is 4, right? 4 feet. Okay, so what is the radius? All right, so we got to complete this triangle here, right? We got to finish up our triangle. There's the radius. Draw that radius. Actually, let me do a little bit better job here. Hold on. Because what I got to do is that radius, I know it has to be perpendicular, right? It has to make a right triangle for me. So I need to do a little better job of sketching that in there. And that's R. And this part from here, the edge of the fountain to the center is going to be R. Let me highlight those radii in green so you do realize that they're both the same. That's a right triangle. So let's set up our equation here. What do we know? Once again, we're going to use the Pythagorean theorem. We know that r squared plus 8 squared equals r plus 4 squared, because r plus 4 is the length of the hypotenuse. Okay, so I want you to do something for me. I want you to pause right here. I want you to finish this problem and the next problem, the next 2 problems. Stop right here, finish this problem, and do the next 2 problems, and then come back and check them. Alrighty. So you see this equation is very similar to one that we did just a minute ago. So when I FOIL my right side, I get r squared plus 8r plus 16. And then of course these r squares are going to go away because when I subtract it from one side, it'll just leave me with a 0 on both. Subtracted from both sides, it leaves me with 0 r squared on both sides. And so then finally I solve it and I get r equals 6 feet. The radius is 6 feet, radius of that fountain. All right. Next one, I have to use the theorem that tells me since these two tangents share a common endpoint that's outside the circle, I know they're congruent. So I set up my equation accordingly. X squared plus 24 is 49, and then when I solve that, I get x squared is 25. So when I take the square root of both sides, I get x is plus or minus 5. And then I almost said, well, wait a minute, x can't be negative 5 because a side length can't be, a length can't be negative. However, if you look carefully at this picture, it's not telling me that x is a measurement, a part of this. So if I plug in negative 5, I actually, let's see, if I put negative 5 in here, I get 25 plus 24, which is 49. So the positive and the negative both work in that situation. All right. Same thing up here. I've got two tangents to a circle sharing a common endpoint outside the circle. So just as I did in the previous problem, I set those two tangent lengths equal. And once again, I have to take the square root of both sides. I get x is plus or minus 3. I did come over here to make sure that negative 3 doesn't give me a negative answer. And it does not. It gives me 15. So whether I plug in positive 3 or negative 3, well, wait just a minute. Hold on one second. Let me check this out. If I plug in positive 3 here, if I plug in positive 3 right here, I get 4 times 3 plus 27. So that's 12 plus 27. I get 39. What about if I plug in positive 3 in the bottom one? I get 5 times 9 plus 4 times 3 minus 18. So that's 45 plus 12 minus 18. So that's going to be negative 6. 45 minus 6 is 39. So yeah, so it's good. Both answers do work. Have to check those things when I get negative answers because I'm not sure that negative answers always work in geometry. All right, finally we're going to finish up with a proof here. Going to put our statements, our reasons. Going to go ahead and write down the given statement first. BC is tangent to circle A at D, and DB is congruent to DC. All that is given. So let's look at the picture and what we're trying to prove here. BC, so here's BC right down here. It's tangent to the circle at point D, and DB is congruent to DC, and I'm trying to prove that AB is congruent to AC. So it looks to me like what I'm going to need to do is prove these two triangles are congruent, right? That triangle right there looks like I got to try to show that triangle ABD is congruent to triangle ACD. That's what I need to do. I need to prove that. So how am I going to do that? Let's see. Well, I remember, right? Since BD is tangent to this circle at point D, and AD is a radius, that makes these two things right angles, right? Because it means that BC is perpendicular to AD. So I believe that probably needs to be my next step here. I need to say BD is perpendicular to AD. And how do I know that? I know that because of the theorem I learned today that says if a line is tangent to a circle, then it's perpendicular to the radius at the point of tangency. That's a lot. Sometimes we just have to write a lot because there's no name for these theorems. If a line is tangent to a circle, then it's perpendicular to the radius at the point of tangency. Okay, so the fact that those two lines are perpendicular, or those two segments, lets me know that angle ADB and angle ADC are right angles, right? And how do I know that? Because of the definition of perpendicular lines. You can go down and write into your summary area here. That's what we're going to have to do. Okay, so now, since we know that BD is congruent to CD, we've got a side and an angle. Oh wait, we didn't say they're congruent. Almost forgot that. I got to say that angle ADB is congruent to angle ADC. And of course I know that by our old friend the right angles theorem that says all right angles are congruent. And then I'm just left with one thing. I need that side AD. So I'm going to say AD is congruent to AD by the reflexive property. And now I can come up here and grab that. That's what I needed to get to all along. And that is that triangle, what did I call it? ABD is congruent to triangle ACD. And how do I know that? Because of side angle side. Side angle side. Congruence theorem. And finally, AB is congruent to AC. Isn't that what I'm trying to prove? Yeah, AB is congruent to AC because they're corresponding parts, right? AB is congruent to AC because they're corresponding parts of congruent triangles, and I know that means they're congruent. So that finishes that proof. Also, for tonight, I need you to listen to the next little lesson on chords and arcs. So go ahead and watch that.